The atmosphere has more than a chemical composition. It also has structure. That structure is driven by a number of factors and is incredibly important for energy and material exchange between terrestrial ecosystems and the atmosphere. The authors state that atmospheric pressure and density decline with height above the Earth's surface. And this change in pressure and density is one of the things that begins to set up the structure of the atmosphere. Pressure is related to the mass of the overlying atmosphere. So if we take a look at the Earth's surface, for example, there's a lot of atmosphere above it, and so pressures can be relatively high. And then as we go up and up and up, the amount of atmosphere above it declines. And as it declines, the amount of pressure declines too. So when you're relatively close to the surface of the Earth, pressure is high, and as you go up and up and up, so for example, if you're at the top of a tall mountain, there would be a lot less air pressure up there than there was closer to sea level. These changes in pressure are very important for setting up some of the dynamics of circulation within the atmosphere itself. So one question is, does it necessarily get colder as you get further away from the surface of the Earth? We know that pressure is going to decline, but does it uniformly get colder? This here is a diagram, it's figure 2.4, that shows the patterns of air temperatures with height. And you can see that there's a couple of things that are important here. The first is going to be the patterns of temperature. The x-axis here is temperature in degrees Celsius, ranging anywhere from 30 degrees Celsius on down to negative 90 degrees Celsius. And this height is in kilometers, 10 kilometers, 20, 30, 40 kilometers, for example. And what the authors have shown are the four major layers of the atmosphere. The first one is called the troposphere, and it's the one that's closest to the Earth. The second is called the stratosphere, which is the second most closest, and two others, the mesosphere and the thermosphere, which we won't discuss much here at all. So as they show the 1, 2, 3, 4 layers, in between those layers are pauses. So the tropopause is between the troposphere and the stratosphere, the stratopause between the stratosphere and the mesosphere, and they also show temperatures. So you can see within the troposphere, the further up you go, it gets colder and colder and colder. But as you enter the stratosphere and you continue to go higher, it actually gets warmer. So the density of air is less and less and less, but the temperature of that air actually continues to go up. We'll review why that is in a second, but we're going to start with the troposphere. So the troposphere is the lowest atmospheric layer. And 75% of the mass of the atmosphere is in the troposphere itself. And the troposphere is heated primarily from the bottom. Most of the energy that's absorbed by terrestrial ecosystems, for example, or oceans, gets radiated as sensible heat flux or as latent heat flux, enters the atmosphere that way. And so that a lot of that heating is at the surface. And the further up you go, the more energy release there is, but also the colder and colder it gets. Because air heated at the surface cools as it rises and expands, the temperature decreases with height. And so that expansion of air itself absorbs heat and generates a cooling of the air as it rises. Now the troposphere is important for a couple of different reasons, but essentially this is where most of the weather occurs. So most of the variability that we get in rainfall and in temperatures occurs within the troposphere. And the stratosphere, for example, is a lot more constant. Now the tropopause, as we said, is the boundary between the troposphere and the stratosphere. And it occurs at a height of roughly 16 kilometers, at least in the tropics. In the polar regions, it's a little bit shallower and it's only 9 kilometers. So it would be roughly here in the polar regions. And that height varies seasonally. It's driven a lot by the energy dynamics, for example, of the surface of the Earth. But we're talking roughly 10 to 15 kilometers in height. Now, within the troposphere is what we call the planetary boundary layer. And this part is really important because it determines really where the exchange between terrestrial ecosystems and the atmosphere is circulated. The planetary boundary layer the authors define as the lower portion of the troposphere in which air is mixed by surface heating. and it creates convective turbulence, and by mechanical turbulence is air moves from the Earth's rough surface. So this here is an example of the planetary boundary layer coming from in the Amazon basin. In the morning, the planetary boundary layer, the relatively still air adjacent to the surface of the Earth, in the morning it's relatively shallow. And then as there's more and more heating, for example, that planetary boundary layer increases. The increase in surface temperature drives evapotranspiration and convective mixing, and this causes the boundary layer to increase in height until the air becomes relatively cool and that water vapor condenses and the clouds form. So if you notice also, as far as the scale of the y-axis is concerned, we're talking roughly 1 to 1.5 kilometers in height. So when you go to a place and you look up and you see cumulus clouds that look like that in the sky, that roughly tells you the height of the planetary boundary layer. And the cumulus clouds, the bottom of those clouds, they're flat because they're sitting atop the planetary boundary layer. And this is generally somewhere on the order of a kilometer. So when you look up into the sky and you see cumulus clouds, you can estimate that they're roughly a kilometer. The bottom of those clouds are roughly a kilometer in height. This here is another diagram that shows the top of the planetary boundary layer midday. Here's the Earth's surface. In miles, it's roughly half a mile or a kilometer. And you can see this shows the relationship of the planetary boundary layer with the rest of the troposphere and the tropopause. And so a lot of the clouds too, what you'll see is that the bottom of the clouds, for something like a cumulus cloud, sits on top of that planetary boundary layer, and the top goes all the way up to the tropopause. Now up above the tropopause is that next layer of the atmosphere, and that's the stratosphere. The stratosphere is unique in that it is heated from the top as opposed to the bottom. And as a consequence, the temperature actually increases with height, and that's shown right here. So the bottom of the stratosphere is often really cold, but by the time you get to the top, it's warmed up and it's almost 0 degrees Celsius. Now the reason it's heated from the top is that there's a source of heating right here in the upper stratosphere, and that's the absorption of UV radiation by ozone. So we talked about how ozone has a very strong absorption band within the UV, and that absorption of the UV through a couple of different mechanisms releases a lot of energy and heats that portion of the atmosphere. So the reason why we get heating of the upper stratosphere from ozone is we have a lot of oxygen there. UV light hits oxygen and creates a free radical that then binds with oxygen to form O3. And so that's what generates the ozone at the top of the stratosphere. Stratospheric ozone is most concentrated in the upper atmosphere, and that's where most of the heating occurs. And that's driven by the availability of shortwave UV radiation and the density of oxygen. So we have a lot of oxygen here, relatively, and a lot of UV radiation hits right here too, and that generates a lot of ozone. That ozone absorbs the UV and eventually releases a lot of that as heat. Now, as I said, there's two other layers that we think about, the mesosphere and the thermosphere, and the authors state correctly that the mesosphere and the thermosphere have relatively little impact on the biosphere. So the patterns that are there are important for atmospheric scientists to think about, but as far as an ecosystem ecologist, it doesn't have much impact on the types of things that we think about. So thinking about the troposphere and the stratosphere and what the patterns are of temperatures and pressures are concerned, and what happens within the troposphere and the stratosphere are really our main concerns here.